Thank you so much for giving me this opportunity to present a research paper. So as you can see, my research paper name is a collaborative empirical analysis on machine learning based disease prediction in healthcare system. So we all know that nowadays machine learning is the method that is going on very much, right? Everywhere you can just predict anything using data. So I think this has really impacted a lot of systems and a lot of fields. Like you can get so much out of the data and see. So I think medical has been the most impactful. What I see that because it really gives you the more of health and that really contributes to the people and the population. So a little bit more about introduction. You know that nowadays global health concerns are increasing. We just I think went over like COVID, right? So I think that really raises a concern how we can just simplify and how we can use machine learning approaches and analyzing data to prevent some these kind of things in future. And in this thing, AI is going to play the most important role in transforming the healthcare and may be helpful in predictions for the upcoming like health issues or maybe the pandemics and the epidemics. In this presentation, I'll be using the comparative analysis of 4 machine learning basic algorithms for disease prediction. This is a very basic thing. Like first, we should be able to see that whether the thing is going to happen or not by analyzing their symptoms. So I have used 4 ML algorithms where they'll be analyzing, okay, which method was able to predict the disease prediction for the patients. Okay, so the next is the data overview. So in this data, they had almost 5 diseases. You can see that pneumonia, tuberculosis, GERD, hepatitis A, and hypertension. So what they have done is they had almost 132 symptoms for all of them, and they have taken out the unique out of them. Like for pneumonia, they have taken vomiting, chest pain, loss of smell, fast heart rate. So these are the 4 symptoms that were very unique for pneumonia. Like they all should be there to have the prediction of pneumonia. For the tuberculosis, you can see it's chills, blood in sputum, muscle pain, vomiting. So all of these, how the data is organized is like, if you have a symptom vomiting, so it will say 1. And if you don't have any symptom of vomiting, it will give a 0 under pneumonia. Like, okay, you have a 0. So these all are binary numbers in the data set, like whether it's a true or a false thing. For tuberculosis, like if you have chills, then you say true, 1. And if it's not there, then you say 0, you don't have. Not all the patients are going to suffer from all of these symptoms, but these are the most common and the majority the data set patients have seen. So little bit about the machine learning algorithms that have been used in this paper are KNN methods, naive Bayes, decision tree, and random forest. So a little bit about these machine learning algorithms is like, these are very basic one. KNN is like, what it will do is like, if you have a prediction, like you have a disease, then it is going to see, okay, it will have the other points of symptoms around it. If most of the points surround that thing, right? So that means you are going to have tuberculosis or the disease prediction. Like it's basically measuring the distance or maybe the clustering around the tuberculosis or some other disease. And in naive Bayes, we are mostly working with the probability. It's a like where you're just seeing all of the symptoms and calculating the probabilities. Decision tree and random forest, they both are very much linked to each other. In decision tree, what it does is it starts from one root, like you can say it can take one symptom and then it narrow downs to other symptoms. It starts from one, it sees, okay, which one is the major one. And then by saying, okay, if this exists, yes, then go to this symptom. If no, then go to this symptom. So it's basically creating a tree-based structure. And random forest is the modification of decision tree. What it does is in random forest, we are creating multiple decision trees, not just the one decision tree. What it does is it learns from one decision tree, then it creates the updated decision tree so that we can have an accurate prediction of the disease, right? You're not going to have always the correct prediction, but it's machine learning is like, okay, we want to have the maximum probability, like what we want in our data, or we want to have the, okay, what is the maybe closely 95 accuracy or 97, or right, it's our main goal to increase. So we keep on modifying, and random forest is the modification of decision tree. It's a iterative decision trees. So next, going into workflow. So what we do in data, right? So when we have a data and everything, what is our going to be approach? So that is discussed in this model workflow. If you see under A section, that is like, okay, we have a data set, then we have a data pre-processing. Data pre-processing means like, you are not going to have a structured data, and you're not going to have the proper data set. You have to deal with so many things when you're working with the data. You might have a missing values, you might have a outliers, right? Outliers means like some all the things are falling together, but one or two are apart from it. So we can neglect those things because that can impact our prediction. After processing, then the machine learning part comes. I think in the model workflow of machine learning, right, most of the major thing you have to do is data pre-processing and making your data relevant for machine learning. If you don't do any pre-processing, I don't think so machine learning models are going to perform well. You really need to have a relevant information to get into the machine learning, because it will read or it will study itself what is provided to it. So if you want to have a meaningful insights, you need to have a proper data set, properly done things so that it can predict things accurately. So after the data pre-processing, what it does is like, you're going to split it into two parts. So your data is going to split into two parts, that is training set and the testing set. If you see, training set means 80%. So what is training set? What we are going to do is we have the symptoms and we know whether a person had a disease or not. Yes or no, right? 1, 0. So in this, we are making everyone learn, okay, what this is the process and this is the outcome. Machine knows the outcome. It sees everything, it learns, okay, what is the pattern it's following, and it creates some kind of equation or some kind of a model that better explains the relationship between the symptoms and the model, like the disease prediction. So we are using, first we'll do it like for KNN. First it will see using KNN algorithm. We'll give the data. It will see what is the algorithm behind KNN. It is going to set up something related to, like reading data and seeing, okay, this is how in KNN is it's working. And then it's the same thing for your Bayes decision tree and random forest. After it will create these algorithms, we'll be having four algorithms because we used four methods for all of these, right? So what now, since you have an equation doesn't mean it is going to be true. You have just set up a relationship. So in testing set, what it does is we are verifying. That is called verification. What we are doing is we will not do anything, like we'll just give symptoms. We are not going to give, okay, whether a person had a disease or not. We will just have no entry over there. What we want to do is whether it was able to predict it or not. Since it will give us some prediction based on the already the calculated algorithm, then we'll compare that with the actual value we already have. And then we'll see whether it predicted correctly or not. That is called testing. After testing the model, now we'll have some kind of verification, something, right? But we want to know, okay, how our model is performing. What is the model evaluation? Right? After testing, we have to evaluate our model. We have to choose some kind of matrix to see what is the accuracy, what is the precision, right? How many things were wrongly predicted, because it will predict wrong things too. After doing that evaluation, you'll have some kind of, confusion matrix is used for comparison. That is used for mostly, okay, out of how many correctly predicted wrong were predictions were there, to calculate all of those matrix. Once we have done all of these things, then we assemble our model, right? And then it's like you can see that ensemble input, you give some input, that is like now you are entering new data. That is basically input means now it has done something with the data you have provided. Now this is input, means you're doing something new, you're adding some new thing into model, and then it will give you the prediction, whatever it has learned from the data. And then you have the output, whether you have a disease or not, or maybe what is the probability. And this part B is most of how it's going to work in the real life system, like how you're going to have this, you sometimes companies build sites, like you must have seen, like, if you put your weight and put your height, then it calculates your BMI, right? This is how the part B is showing. Like there is some algorithm going, it will ask some question, do you have these symptoms? And then you say, okay, you might have a COVID or not, or you might have this disease or not. So this is whole thing that is in real time working. You might not able to see the workflow, but yeah, you'll be able to have the prediction. So after that, this is the comparative analysis of algorithm. Like I've told you about, like we have the four methods, right? And what was the prediction of all of these diseases it has given? You can see that for KNN, you have 92.50 accuracy, right? 87, then 95.83, 99.60. So accuracy means, like, you are calculating what were truly, like whether you had a true disease, whether you did not have it predicted correctly, divided by the whole number of observations you had. So that means if you had 100 entries in your data, it predicted 92 correctly. And if you had like 87 for naive and 95, approximately 96 out of 100, and then random forest was pretty close, 99 were predicted correctly out of 100. And in precision, like you can't always rely on accuracy when you're comparing the things. You might have a disabled data or imbalanced data. So you need to see so many other metrics to evaluate what is with other things. So precision is like, like how many were correctly predicted, and how many correct, like prediction, like you had a disease, but it predicted you did not have the disease. So that is precision. And recall is the same with the true prediction, but how many were positives, but it gave the negative result for recall. And then F1 score is the combination of precision and recall. Higher the score of F1, the better your model is. That is the basic statistical metric you use for the evaluation of your model. After that, you can see it's called tenfold cross validation. So in this thing, like I've told you, right, like this is what we have gotten from testing and trading. So cross validation is like, and that we had 80% training and 20% testing data. But in cross validation, we are not just particularly focusing on 80% and 20%. It will manipulate data for 10 times. Like it will change the matrix again and again, and it will see, okay, 10 times you'll have 80%, 20%, 80%, 20%. So it will give the mean solution. Like if you see, random forest had a still 99.19% training accuracy, and with the standard deviation. Standard deviation means 10 times when you did with the training data set, the variation of accuracy was accordingly 0.44. Like there was not much variation. Same thing with the testing data, 98.58, and standard deviation was 1.31. So if you can see from all of these, random forest worked pretty well according to this data set. And I would really like to mention about this thing. It's not required that random forest is going to predict always the same, like for always same result like on other data sets. You might have the other algorithms performing well on other data. For this particular data, like whatever we have the symptoms and everything, this model works well. Like if you have this kind of data, you have this kind of symptoms, random forest performed well. So I would like to conclude by saying the same thing, like, okay, random forest had the accuracy, but it is not implemented to all of the other data. So you have to go through everything, having your own inclusions, right, and exclusions. And future work on this paper was to, like, add more data to it. Like, I think more data you have, the more patterns you can observe, and it will give you the more accuracy. Like Rather than having 20 entries, if you have 100 entries, you will get to know more about things, more about patterns. And you can include deep learning techniques. This is a narrow down version of machine learning where you work with the neural networks, and it's a very complex thing, but the accuracy of getting these deep learning techniques are very much popular, and I think it gives a lot of accuracy when it comes to disease predictions or maybe the classification models. Yeah, so in the end, I would like to thank you for giving me this opportunity. And yeah, if you have any questions, do let me know.
I think you did a fantastic job. Would anyone like to ask some questions about her research that she dived into and shared with us so we could learn something as well?
Yeah, I just want to know, like, as someone who works in like healthcare, so I was just wondering if like the experiment that you discussed in your paper also covers in like any inherent biases that may happen as well.
So in this, it is particularly based on one country the data has been collected from, right? So
Mhm.
like if they have like you can have a different like bias is based on like you can have a different for different countries you might have a different symptoms too sometimes, like or sometimes it's genetic too. So I think it varies from geographical things. But other than that, you can have a maybe if you had a lot more data, because they had, I think, approximately lesser data compared to for the study. So if they had the more data, they would be more get to know about okay what kind of biases could be there. But for now, I would say it was just more of geographical thing. It was based on just one particular place the data was taken from.
Okay. So would the results differ if you do it like in another country then?
Not mostly. Like if you might have a difference if you include some other kind of, other symptoms. If you include some other like, right, some people have exceptions. Even in the same country also, they can have a different thing. So I think it's better to understand what the uh, other columns could be the most relevant. But once for this, I think these were the very basic diseases they have included. And I think pretty much it's the same thing in every, like worldwide. There could be exceptions, but I think these are the very common ones.
Okay, yes, gotcha. Yeah, thank you.
Do you think that there are any like innovations or improvements that this paper added to the field in the area of predicting disease and sickness and things like that? Did you
So
have any cross references? Yeah, I was just curious.
in this particular, no. In this particular paper, there has not been that much. But I think like other people might have done their research too, right? Maybe before and after. They might have included some new factors. Like they just had, I think, approximately four symptoms. They had just taken out the four common and the most ones, like people have like one out of 132 symptoms, they have taken out those like four symptoms for each disease. So maybe they could have taken some more also, or because I think severity for other every person is different. Some people might have a more headaches compared to other people. So I think there could be the modification, but what they can do are like they can just rank out based on okay what was the severity for each person. I think that could be the modification, but I did not come across.
Sure. That was fantastic. We really appreciate your time and willingness to share your learnings with us. Yeah, it was excellent.